Good morning, everybody, or I guess good afternoon or good night, depending on when you watch this. But if you're new to my channel, I basically break down Calculus 1 and 2, or Calculus A, B, and BC concepts. Over the summer, I'm planning to sort of sequentially go through every single unit of the AP Calculus curriculum. So if you want to see more of that, stay tuned. But today we're gonna be skipping Unit 1 because it's limits and continuity. I trust you guys can figure that out. But today we're gonna be starting with Unit 2, which is all about derivatives. Okay? So, what is it? I'm not sure why I did that. There we go. Okay. So, first question, right? Most important. What is a derivative? Okay, so a derivative is like the textbook definition, if you look it up, is that it's an I don't know if I'm going to spell this right, instantaneous rate of change, okay, or an instantaneous slope, right? So let's think about this for a second. What does that even mean? Okay, so let's say you have a function f of x, right? And this could represent, so many different things. It could be like, the amount of water in a tank over time, or, a particle's position with respect to time, or like the fluctuations in the price of the stock. It could be basically anything you can model with a function f of x could represent, right? So what is the derivative of f going to tell us about f? Well, that's a great question. So, let's say f, oh my god, okay. Let's say f is a line like this, okay? Being a line means that for every increase in x, right, you're going to see a proportional increase in f, okay? In other words, there's a direct relationship. The more you increase x, the more f is going to increase, okay? And that's constant throughout the entire line. And what do we call that? We call that the slope, okay? Or m, if you remember from algebra, okay? So the slope of a line is essentially the rate of change of the output divided by the rate of change, or no, I'm sorry, the change of the output divided by the change of the input, okay? Now, this gets a little more tricky if you were to try and analyze how quickly something with a curve is changing, okay? Let's say a quadratic, right? And the reason why it gets tricky is because, well, look over here, right? If you just isolate this section, this seems to be increasing rather slowly, okay? That's not a very steep line at all. But if you look over here, this is now much steeper, and it's going to keep getting steeper because you see this is trending upwards, so it's going to keep getting steeper as x increases, right? So what you see here is not a constant slope, but a variable slope over the entire line, right? And that is, bothersome because we can't use this sort of m equals change in f over change in x formula, because at every single point that slope is going to be different. If we can't use this to find exact slopes, but we can use it to get an approximation, okay? So like between these 2 points, okay? I'm so bad at drawing lines. So if we use these 2 points, okay, similar to how we do with a line, right? With a line, we pick 2 points, calculate the difference in f over the difference in x, and that would be your slope for the entire line. But we can't do that here, right? But we can use it to approximate. So we pick 2 different points, right? Same process. And we sort of imagine there's a line between them, even though we know there's a curve. And we take the slope of this line, okay? So if we were to do that, what would it look like? Let's find out. Here, let me make some more space. Okay, so our first point, right? We're going to let this be x, okay? And then we're going to say the interval between the 2 points is h, okay? Which is going to make this x plus h, all right? Because this is x, the output at x is just going to be f of x, and the output at x plus h is going to be f of x plus h, all right? Now, if we apply our slope formula, right, change in f is f of x plus h minus f of x, okay? The change in x is going to be x plus h minus x. Now you'll see very quickly, x plus h minus x is just h, okay? So this is going to give you your slope of the secant line, okay? This is a pretty great approximation of the slope at all of these points in between, but it's not going to be exact. And that can be a problem in many, many different contexts where you're looking for exact answers, okay? So how do we make an exact statement about the slope at some random point? Let's say we're looking for the slope at this very point, okay? Not the whole segment, just this point. Well, what we can do is essentially move this point closer and closer and closer and closer to this point. But we can't let them be the same point because then this whole formula breaks down, right? If we let them be the same point, then h equals 0, right? Plugging in h equals 0, you have a divide by 0 error. That would be undefined. And that you can't really do anything with that, right? So we're not going to make h 0, but we're going to make it trend towards 0. We're going to make it really close to 0. In other words, we're going to take a limit as h approaches 0, okay? And this is, this is extremely, extremely important. This is going to be your general formula for a derivative. Okay? So this is where this formula comes from. It's going to be extremely powerful, but there's other things that we can, other rules per se, that we can extrapolate out of this formula. Okay? Let's use this formula on some example function, all right? Quadratic. Okay, we were analyzing a quadratic here. Let's say we have a quadratic. Okay, f of x equals x squared. Okay. Applying this formula, we have f of x plus h is just going to be x plus h all squared minus f of x is just going to be x squared divided by h. Okay. Well, simplifying this bit, you have x plus h squared. You should know that this is just going to be x squared plus 2xh plus h squared, right? So really, we're just taking the limit as, this should be an equal sign, limit as h approaches 0 of x squared plus 2xh plus h squared minus, minus x squared, right, divided by h. And you'll notice these two x terms are going to boil out, right, because you have x squared minus x squared, that's 0. So limit as h approaches 0, right? We're going to evaluate this algebraically. Okay, I'm sorry. Because if you try to directly substitute this in, you're going to run into an issue because you have literally 0 divided by 0, and that doesn't tell you anything, right? So we're going to evaluate this algebraically. So you have 2xh plus h squared divided by h, right? 2xh divided by h is going to be 2x. H squared divided by h is going to be h, right? Taking the limit, there is no h term in here, so this is going to remain unchanged, and limit as h approaches 0, h is just going to be 0. So in other words, the derivative of x squared is going to be 2x, okay? And there's a couple different ways to write that. So this is where you get into the notation, right? So here's the first way. So it's just an apostrophe, right? The second way is df dx. This is sort of a reference to the whole delta f delta x slope definition. It's kind of similar to that. You can also write f dot. That's more, this is usually only used when the input is time, but this is much less common. Most of the time you're going to be sticking to either this for this. Okay, so I'm going to use this one. So df dx is 2x. Okay, and if you want to not write f, if you want to explicitly state the function, then you just write it like so. ddx of this is 2x. Okay, so there's a worked out solution for the derivative of x squared. And now let's talk about different interpretations of the derivative, right? So as we spoke about, it's sort of the rate of change or the slope of this function at a singular point, okay? And if you think about it, what we're doing here, let me make a new axis. When we take the slope at this singular point, right? And if we apply the limiting process, all we're doing is taking a slope between these 2 points as this gets closer, right? So when this sort of collapses onto here, we're taking the slope of this line, okay? In other words, the line that only touches this function at this very point that we're looking for the slope at. So this is going to be your tangent line. Okay, so the derivative can also be interpreted as the slope of the tangent line. Okay. In some physical contexts, right? Let's say you have a particle. Particle is moving back and forth as per some function f of, or let's say x of t, right? Because x represents position. So the position of the particle is x of t. Taking the derivative of this, right, dx dt, that's going to give you, that's going to give you the rate of change of position, right? And you should know, rather, that the rate, even if you don't know, that's fine. But the rate of change of position is going to be velocity, right? You might have seen this formula, right? Velocity is change in position over change in time. This is just that stated more accurately, okay? So this would be sort of an average velocity, where this is an instantaneous velocity, okay? So it can be used in physics contexts to get you your velocity. Applying the derivative one more time to velocity, right? Well, that, if we think about what this represents, well, that's just acceleration. So the derivative of velocity with respect to time is going to be acceleration. Instantaneous, of course, right? And if we want to sort of express acceleration as, a form of x, right? Well, what are we doing here? We're taking the derivative of velocity with respect to time, which itself is the derivative of x with respect to time, right? So the way we write this is called the, so when we take the derivative once, this is called the first derivative. If we take it twice, that would be your second derivative, right, intuitively. And you'd write it sort of like this. Okay, this is the format. d squared x dt squared. Okay. Now let's talk about differentiability and continuity. Okay, what the relationship is between the two. So any sort of continuous, any function that's continuous everywhere, right? Say something super smooth like this. Visually, you can see that at every single point, there's only going to be one tangent line, okay? So this is going to include, your sine, cosine, all of the polynomials, any exponential, they're all going to have this smoothness to them, right? And that's going to allow you to take the derivative at any point. In other words, the fact that you can take the, And the other thing to note, right, is if you can take the derivative at any point, that means, the value must exist at that point and around that point. right? And that turns out to be the exact definition for continuity. So if something is differentiable, that implies continuity, right? Because, for example, if you look at something that's not continuous, okay, there is absolutely no way to take the slope at this point because the value of the point doesn't exist, right? You have nothing to plug into this f of x expression at this point, okay? So if the function is differentiable at a point, that means it's also continuous at that point. However, it does not go the other way around, okay? And once again, differentiability is just the property of a function that the derivative, the first derivative rather, exists at a particular point. So that was kind of long, but basically it just means you can take the first derivative, like it exists. Okay. Differentiability implies continuity, but continuity doesn't necessarily imply differentiability, right? And you might ask me, like, why is that the case? Well, if you have something like the absolute value function, right? Oh, come on, straight lines. Okay, that's straight enough. Absolute value function, right? You will notice that this is not smooth at this particular point, okay? It's a hard turn. This is what we call a cusp, okay? So the fact that it's not smooth, notice that you can sort of draw you can draw a number of these lines, right? In fact, you can draw infinitely many tangent lines. So how do you know which one to look at to take the derivative, right? Because the derivative sort of operates on the assumption that there's only one tangent line, because that's the tangent line you're taking the slope of. And the answer is you can't, okay? So cusps, or sharp turns, are not differentiable, okay? And this is more clear when you actually break this down into its components, okay? If we were to write f of x equals absolute value of x as a piecewise function, it would look something like this, okay? For x is less than or equal to 0, we have f of x equals negative x, right? I'm not sure if this is the correct notation, but bear with me. And if x is greater than 0, f of x is then going to be positive x, right? So then if we take the derivative of each piece, right, you have the derivative of negative x, well, that's just the slope of the line negative x, right? The slope of the line negative x is just negative 1, right? Y equals mx plus b. In this case, our m is negative 1. Same thing applies here, right? The slope of this line is going to be positive 1. So what you notice is that in this case, where you have both of them, like if you take the value of f of x at 0, you have the leftward piece is going to be 0, and the rightward piece is going to be 0. But if you take the derivative now, the leftward piece of the derivative is always going to be negative 1, and it's going to be negative 1 at 0, but then it's going to jump to positive 1 after 0. So this is going to be a jump discontinuity. In other words, the derivative at this point is not actually going to exist. Okay, that was a lot of talking. But bottom line, right? The derivative is an instantaneous rate of change. It represents the slope of the tangent line, and the formula for it is going to be right here. Essentially, we're just taking these 2 points along the line, approximating the slope between them, and then making the space between them approach 0. These are your notations, right? F prime, well, you pronounce this F prime, but it's really F apostrophe. This is going to be df, dx, 2 different notations. Both are used very often. Derivative of position is velocity. Derivative of velocity is acceleration. And then the second derivative, you could say, of position is acceleration. And finally, differentiability implies continuity at a point, but continuity doesn't necessarily imply differentiability. Thank you for watching. I will be back very soon, most likely within the next few days, to discuss the rest of Unit 2.